In this video, we're going to explore tying equilibriums of acids back to some old info from 162. In this case, I've got this set up, a flask with some water in it. It's got a device inside that can spill a sample into that water. It's got a balloon attached at the top. In this way, we can have a solution of pure water reach equilibrium, its vapor pressure exerting inside that balloon, and then, well, we can shake it or twist it and somehow dump all that lactic acid into the solution. And so our green lactic acid will get dumped down, it'll spread out down the water and become part of the solution. In doing so, we will introduce a solute into our water, and thereby change the vapor pressure. As a result, well, some of the water particles that had been bouncing around inside the balloon settle back into the water. And so our volume of our balloon will change from 1.75 liters by just a little down to 1.74795 liters. Using that change, we're going to solve the Ka of lactic acid. Now, we're making a few assumptions here. One of them is that lactic acid breaking into H plus and its conjugate base, that these individual species act as the only species in solution interfering with the vapor pressure. We're not worried about any solvation effects or other things. So it's a little simplified, but this is what we're going to assume as we attempt to solve the Ka from this slight change in the volume caused by a change in the vapor pressure of our solution. Well, how are we going to go about doing that? Well, first thing is, I've got a gas, well, probably some gas law info. How much did I change my gas by? The whole idea is a few bits of water vapor that normally would bounce around, now settled back down below and can't bounce around anymore. So how much of our gas was that water vapor? How much was lost to make this get smaller? So let's look at the change in moles. Well, remember our PV equals nRT. So we can find our initial moles. So let's find N initial. It's going to be PV over RT, 760 torr, 1.75 liters. R for when we're in torr is 62.36. And our Kelvin at 25 Celsius is 298.15. So our original moles in our balloon was 0.071534. We're just going to keep a lot of more sig figs than we rightly have for a while. That was our initial moles. Well, the N final, that's still going to be PV over RT. The only difference is our volume changed. It's still 760 torr out today. And if you got a balloon, remember your pressure inside your balloon is going to be equal to your pressure outside. I suppose we could account for the stretchiness of the balloon, but we're making the assumption that stretchiness doesn't affect our pressure here. And so our internal pressure of the balloon must equal the outside pressure. So it must be 760 still, but it's just smaller. It's 1.74795 liters. That's where our smaller amount of moles is going to come from. Slightly smaller value on top, so slightly smaller calculation. Because our R value doesn't change, it's still 62.36 for torr liters over mole Kelvin. And the temp is still 298.15. 0.07144499 final for a change in moles equal to 0.000083796 or 8.3796 times 10 to the minus 5. So we didn't lose very many moles. A tiny bit of water vapor trying to escape from the water up into the gas phase, like that vapor, doesn't occur once we mix the lactic acid in. Lactic acid blocks some of those escapes, a few less water molecules per time unit escape, and the net effect is, in our balloon, we lost this many moles of water vapor. Well, we're also talking about changing the vapor pressure. That's the whole reason our moles are decreasing. So what vapor pressure were we working with? What was our original vapor pressure? Remember that if you've got a vapor pressure, we can use the equation that the natural log vapor pressure at whatever temp divided by the vapor pressure at another temp must equal the delta H of vaporization over R times the differences in the temperatures. Well, it's pure water, and we do know the vapor pressure at sea level under standard pressure. Water boils at 100 degrees, which means its vapor pressure must equal the external pressure, which is why we chose 100 here. I can plug in some values. The natural log of the vapor pressure at 25 Celsius is going to be over the vapor pressure at 100, which is 760. Our vapor pressure at the boiling point of water must be equal to sea level standard pressure, so 760 torr. Well, that must be equal to our delta H of vaporization, which was 40,700 joules, or 40.70 kilojoules per mole, divided by our gas law universal R constant, in this case 8.314 joules per mole Kelvin. So this time we're not doing an ideal gas law, we need the R value for our universal gas constant. Well, our temperatures are 1 over 373.15 minus 1 over 298.15. So our higher pressure on bottom and first temp, our lower pressure on top and second temp. Natural log of pressure at 25, so what our vapor pressure should be for that flask, minus the natural log of 760, which is 6.6333. All that should equal negative 3.3001. So we multiply out the right side. We start to separate, multiply out the left side. We add 6.6333 plus 6.6333. The natural log of the vapor pressure at 25 should equal 3.33322. E to both sides. So e to that, e to that. The pressure at 25 should equal 28.03 torr. That's our pure vapor pressure. So using our Clausius-Capron equation, we're able to determine what our pure vapor pressure should have been. Well, I know the pressure that should have come from water. So prior to adding the lactic acid, I can actually figure out how much water vapor there was. So we find the moles of vapor pressure from water when it was pure. That's just going to be the pressure from the water, 28.03 torr, times that volume it was in, 1.75. So before we added the lactic acid, a small bit of the 760 torr was from water. 28.03 of it was from water. It was spread out in that same volume, so I can find out how many moles of water was in the original gas space. Again, R value 62.36 per liter mole Kelvin, 298.15 Kelvin. All this will equal the moles of H2O gas initially. What pressure would the water gas have exerted in the original volume? We know that. We know the original volume. How many moles of water gas would have been in that volume? We'll find that originally that was 0.002638 mole of water vapor. That is how much water vapor was in our balloon in the original flask. Well, we know how many moles we lost. 8.3796 times 10 to the minus 5 was lost. So I can figure out how much moles of water there was after the lactic acid addition. My moles of water gas initial minus the lost will equal the moles of water gas final. 2.635 times 10 to the minus 3 minus 8.3796 times 10 to the minus 5. 0.00255545 mole of H2O left. Well, if I know how many moles are left in my balloon after, I can plug that back in and find out what pressure they were exerting. I know the final volume. I now know the moles that must be left afterwards, and R and T. My pressure final of the vapor pressure times the volume final must equal the moles final, R and T. Rearrange, solve for that pressure. I'm just going to divide the volume down. What was the vapor pressure of the water gas after we'd reduced the number of moles of water gas? 0.00255545 mole, 62.36 torr liter mole Kelvin, 298.15 Kelvin, divided by 1.74795 liters. That pressure final for my vapor pressure is 27.14 torr. So we reduced our vapor pressure a little. We brought it down. As a result, our balloon had to contract so that the total pressure would match the outside. It had to get smaller so that what gas there was would be in a smaller volume to balance the pressure back out to 760 total. But it had to get smaller because we lost a little vapor pressure. Well, remember that the vapor pressure of a mixture is always equal to the pure vapor pressure times the mole fraction of the species. So 27.14 torr must equal 28.03 torr X of H2O. Divide across, we'll find that the X of H2O, the mole fraction, 27.14 divided by 28.03 is 0.96824. Instead of being 100% water, we added the lactic acid, 1.5 moles of it. It broke apart into particles, and the number of particles it broke into took up part of the solution. Out of that, about 96.8% of it is still water. But now we know that it's not pure water. Now we can figure out how much of it is lactic acid. Well, we have the mole fraction for water. We know we added 1.5 mole of lactic acid, and that was in 1 liter of total solution, and its density was equal to 0.97 grams per milliliter. So we have 1,000 milliliters, so it's 970 grams of solution. Because we know the volume of that solution and we knew the density, we could find the total grams of solution. And we know the moles of lactic acid. If we go look it up, lactic acid, the molecular mass of lactic acid is 90.08 grams per mole. And so if I have 1.500 mole of lactic acid, and for every 1 mole, it's 90.08 grams, we'll find that's 135.12 grams of lactic acid. So of our total solution, 135 grams of it must be our lactic acid, and there's 970 grams total, which means we can find the weight of water, which means we can find the moles of water. I have the moles of lactic acid, and I can find the moles of water. So 970 grams minus 135.12, 834.88 grams of water is the amount of water. Hey, it's 18.016 grams in every 1 mole for water. And so that's going to give us 46.341 mole of water. So I know my moles of water and I know my mole fraction of water. Remember that your mole fraction of something is equal to the moles of that thing over moles total. So 0.96824 must equal 46.341 moles of water over X total. Our X total moles must therefore equal, when we rearrange and divide by 0.96824, 47.8611 mole of particles total. I can subtract from it the water, and whatever's left must be all the other particles that came from the lactic acid dissociation. So minus 46.341 mole for 1.52015 mole of other. So we used our vapor pressure and our volume change to find the mole fraction of water. We then used the weights and the densities to find the moles of water, used that and the mole fraction to find the total moles, subtracted out the water, and we now know how many moles of other things must be present. Well, we put 1.500 mole of lactic acid in, but lactic acid, well, it's an acid. It breaks apart into H plus and La minus. If we start with 1.500 of this and none of the others, how do I get up to 1.52015? Well, I'm going to lose some of this. I'm going to gain some of these. Well, for every one lactic acid I lose, so one particle goes away, I'll make two. So one of these will end up canceling, and it doesn't matter which one, but the net effect is if I subtract 3 and I add 3 and I add 3, 3 and 3 cancel, I just increase by 3 with total. It doesn't matter which ones I'm canceling. For every one initial particle lost, I will gain 2 new ones. So for every one lost, I actually net 1 increase. So I really just have to look at the increase. If I'm increased by 0.02, then 0.02 of these must have fallen apart. Because for every loss of 0.02015, I'm going to gain 0.02015 and another 0.02015. So I go down by that amount, I then go up by that amount, and then another one goes up by it again. So to know that there's this many particles total at the end actually is pretty easy with this dissociation to figure out how much dissociated. It's just the increase from the initial lactic acid, which means I can find my equilibrium concentrations. 1.47985, 0.02015, and 0.02015. So these must be my final concentrations. So my Ka is going to be equal to my H plus, my La minus, over my HLA. Plug those in, 0.02015 squared, they're both the same on the top, divide by 1.47985. All that should equal my Ka. My Ka calculates out to 2.74 times 10 to the minus 4. Real value, the Ka is 1.38 times 10 to the minus 4. So same order of magnitude, a little off on the front number, but we made a lot of assumptions at the start. And so this really wasn't off by very much. A little bit of error for our assumptions and some rounding, but we got pretty dang close to the actual Ka. The idea here was we could tie a lot of different things that we've learned to help us solve one of our new issues. Where does your Ka come from? It comes from that dissociation. When you dissociate, you create more particles. You've got things in solution. The number of things in solution affects the mole fraction of that solution that is water. And as the mole fraction of water changes, the vapor pressure of that water changes. As the vapor pressure of the water alters, there's just going to be a different amount of water that turns into gas, which means we're going to get a slightly different number of particles in our balloon, causing the volume to be slightly different. Tiny changes observed in one location, if we understand how everything connects, can allow us to know quite a deal of information about other components. Just so we don't forget our Clausius-Capron equations and so on. Here was an example where we could tie equilibrium concentrations all the way back to vapor pressure.